Math 110, Exponential Functions and Graphs, Sections 5.2. Now an exponential function is the function of this form, f of x equals a to the x power, where x is a real number and a is greater than 0, and a is not 1. Because if a is 1, it's just going to be really boring really quickly. Now we're going to call that our exponential function with the base of a. Now here are some of these examples of these types of exponential functions we're going to be looking at. 2 to the x power, 1/2 to the x power, 3.5, 7 to the x power, right? It's basically any base to x power where that base is not 1. So this first one, graph of f of x equals 2 to the x power. Now the simplest way of doing this, pick points. Take 0, plug it in. Take 1, plug it in. Take 2, plug it in. And when you plug it in, you're going to get these values. And so these are just the points for that. So I can take those points and I can put them on the graph. Now I'm going to talk about this very, very shortly, but also a property that all exponential functions have. They're always going to have a horizontal asymptote at the equation y equals 0. And that's going to shift depending on certain elements of it, but that's basically where it's going to start, y equals 0, and we're going to go on from there. And so I took all these points, I plotted them on the graph, and so I'm going to get a line that goes in this direction here. Our next example, f of x equals 1/2 x. So once again, take 0, plug it in. Take 1, plug it in. -2, plug it in. -3, plug it in. So you take these values, you plug it in, and you're going to simplify it, right? You get your point here. So I can take these points and I can plug them on the graph. Once again, you can see that I have that asymptote at y equals 0. And so connecting the graph together, you're going to get that statement there. Now this previous graph, we called this graph here exponential growth. And then this graph here, we call this graph exponential decay. Now here are those properties of the exponents, and I mentioned a few of them already. 1, they're continuous. All exponential functions are 1-to-1. The domain is always -infinity to +infinity. The range for a generic exponential function is going to be 0 to +infinity. And so we can kind of take a look at these here. It doesn't cross 0 and it's going all the way up to +infinity. It's increasing if my a is greater than 1. So take a look at these examples here, right? My graph is going up in all of these. This is where my a is 2, the blue is where my a is 3, and the green is where my a is 4. Decreasing if a is between 0 and 1. So once again, this is 1/2, this is 1/3, and this is 1/4. But notice that they're decreasing, right? This is exponential growth, this is exponential decay. Now I have a horizontal asymptote, it's the x-axis, okay? And then that's going to switch depending on certain elements of it. My y-intercept always starts at 0, 1, which is what I have here. Now, this standard form equation, y equals a to the x minus h plus k, we still have this horizontal shift. If you guys remember back from our quadratic equations, our graphs were able to shift left and right. Our k caused our graph to shift up and down. So this horizontal shift is going to affect this starting position here as well. This k is going to affect that starting position there. And it's also going to affect our horizontal asymptote. So just know that these elements are here as well. So k, if it says +2, that means my horizontal asymptote is also going to shift up too. So here you get example number 3, the graph of f of x equals 2 to the x minus 2. So if I were to just take points, plug them in, and I hit my f of x's, I can take that and I can plot it. Now notice this is the original, my 2 to the x. If I took these points and I plot them on the graph, I would get this here. Now notice the reason why I did it this way is because I didn't have any plus k here, so my horizontal asymptote is still at y equals 0. But notice, because this said minus 2, my h was 2, so it shifted over 2. Everything shifted over 2. Everything shifted over 2. And so it kind of verifies that standard form equation that I was talking about. If I had 2 to the x minus 4, I take these points, plug it in, -2, -1, 0, 1, and I get these values here. Now, this being my original with my horizontal asymptote at y equals 0, notice how because of that minus 4, everything shifted down 4. My horizontal asymptote shifted down 4. Okay, instead of starting at 0, 1, it starts at 0, -3. That shifted down 4, that shifted down 4. So everything on my graph shifted down 4 because of my k. Now this example here, it is a little more complicated. Another way that I could write this, as I could say that that's -2 to the negative x power plus 5. So it's easier for us to notice that that right there is our k. So if I were to pick points, and then I have my standard form equation, y equals a to the x minus h plus k. Now notice this is the original. Now two other elements of this is my reflections over the x and y. Because there's a negative in front here, that's going to be a reflection about my x-axis. Because I have a negative in my exponent, that's going to be a reflection about my y-axis. So if the original, I'll do like a little mini sketch, did something like this, then the reflection about the x-axis made it do something like that. Then the reflection about the y-axis made it reflect that way. And so if you notice the shape of this blue one here, it has that same shape here. Okay, it has that same shape there. And so that's why it has that shape. And then my horizontal asymptote was originally at 0, y equals 0, but because of this plus 5, it shifted up 5, and that's why if you notice here, I have that horizontal asymptote there. Okay, but the safest way to do this, plug in values, and it'll verify this type of a direction when you're trying to analyze what the graph is supposed to look like. Now we have E. E, Euler. This value equals 2.7182818284. Now this value, you're going to see it a lot. It occurs naturally in nature, and which is why it could be a pretty important value. A fun thing that mathematicians did said, hey, especially when you're looking at the forms of compound interest, if I said, hey, well, if I wanted to compound my interest yearly, daily, every minute, every hour, every second, when they did that, the value got closer and closer to E. And so that's kind of like a way that they saw E when it came to looking at interest. But the way that we use this is on your graphing calculators or your scientific calculators, you're going to have this E symbol. It's going to say e to the third power. Okay, so you'd literally enter that in your calculator as e up caret 3. And that's e to the third power. And then when you simplify it, it's going to give you that value. You'd enter it as e up caret negative 0.23, e up caret 0. Okay, that's the way you do it. Anything to the 0 power is 1. E isn't immune to that property of exponents. But now when we're trying to graph E, nothing really changes. You're still going to make your t-chart, plug the values in, and then once you do it, you're going to be able to plot your graph. Okay, and notice the properties of exponents are still there. I still have that horizontal asymptote at y equals 0. If originally my graph started at 0, 1, because of that plus 3 there, it shifted my graph over minus 3, so it crosses there. So those properties are still there, but the only difference is my base is now e, which is 2.7-ish. E to the negative 0.5x, create your chart, take these values, plug them in, graph. Because there's no horizontal or vertical shift, the starting point's at 0, 1, and I still have that horizontal asymptote at y equals 0. Now let's look at compound interest. The amount of money A to which a principal P will grow after t years at interest rate R in decimal form, compounded n times per year, is given by this formula. A equals P times the quantity of 1 plus R over n, all of that to the nt power. So suppose that I take $10,000, or sorry, $100,000, it's a lot more, and it's invested at 6.5% interest, and it's compounded semi-annually. So taking that information apart, I should recognize that this is my P, this is my rate, and this is my N. It's compounded semi-annually, which is twice a year. So my rate has to be in decimal form, so I converted that to 0.065. So now I can take these values and I can substitute them into this equation. So instead of writing P, I write 100,000. Instead of writing R, I write 0.065. Instead of N, I write 2. Okay, so all I did was substitute those values in. Then this value simplifies into 1.0325, and I still have that $100,000 in the front. And so taking this to the 2t power, I want to leave it as that t. And the reason why I want to leave it as that t is because it's asking me to write it as a function in t years. So I can say the amount in relation to t, okay, in relation to t. And the other thing is they didn't give me a t, so it's kind of like a sign that I don't really plug anything in yet. So now taking that information, let's find the amount of money in the account at t equals 0, 4, 8, and 10 years. So all I do is take that previous equation that I have, a sub t equals 100,000 times 1.0325 to the 2t, and now I'm plugging in 0 for t. Simplify it. Plug that into your calculator. Plug in 4 for t. Simplify it. Plug that into your calculator. Plug in 8 and plug in 10, and you get your answer. If you have any other questions, please leave them in the comments.